Everybody, thank you very much for attending this talk. That's quite a huge crowd. We're going to do our best to introduce you to our chipStar project. Colin Bertoni worked a lot with me on these slides and on the project, and she's here today as well. So Colin, don't hesitate to speak up if you feel you need to. So, chipStar, a heap implementation for Aurora. Maybe we can start by introducing HIP. So, it's not a HIP tutorial today, of course. So I'm going to present this project chipStar and how you can use it on our machine. But it may be less of a tutorial than usual, and more a presentation of the project, its capabilities, and I would like to have a discussion with you about your interest in using the project and as well, what are your requirements and can we meet them? So HIP is an acronym for Heterogeneous Computing Interface for Portability. It's AMD's portable GPU programming model. For those of you who are savvy with heterogeneous programming models, it's very similar to CUDA. Some would say it's a copy-paste. But it has some nice features that you can directly translate CUDA programs to HIP with a tool called Hipify. And HIP programs run natively on AMD GPU using their ROCm toolchain and LLVM Clang, while HIP programs also run natively on NVIDIA GPU using CUDA and the provided NVIDIA compiler. AMD provides GPU-accelerated math libraries, which are equivalent to CUDA. So HIP-BLAS for cuBLAS, HIP-FFT, HIP-Sparse, and they are wrappers around AMD and NVIDIA GPU compute libraries. So the example is HIP-BLAS is a wrapper around ROCbLAS and cuBLAS. So by design, HIP is supposed to be high performance on both AMD and NVIDIA GPU. So what are the objectives of our HIP on Aurora project here at Argonne? Of course, the goal is to support these HIP applications on Intel GPUs, but the reason for this effort is that two of the exascale systems are featuring upcoming, some of them will feature AMD GPUs. So Frontier, which uses MI 200X, 250X, and El Capitan will use MI 300A chips. So they are both AMD systems, and so HIP is a very likely target for many exascale applications, whereas the pre-exascale systems were mostly using NVIDIA GPUs, so had CUDA support. The transition from the CUDA GPU support to the AMD GPU support goes through HIP mostly, or from a higher level programming model like Cocos. But there is many codes which have been ported to HIP and are being ported to HIP. So the idea is indeed to try and leverage this porting effort on our machine by bringing HIP support to Aurora. So the HIP on Aurora project was originally led by Al Finkel. At this time, we called it HIP-LZ. So if you see HIP-LZ, it's also HIP on Aurora. The goal was to implement HIP on top of level 0, which is Intel's native GPU API for Aurora, but also to support OpenCL, which is a more broadly supported API. Restructure HIP and the HIP ecosystem so we could integrate nicely into HIP, create test suites of code which are interest to ECP, and then support selected ECP applications. Implement the math library we've been talking about previously on top of OpenCL, and also investigate if we can do CUDA support as well. So who is the HIP on Aurora team? The team is a bit disbanded now that ECP is done, but all of these partners collaborated on the project. So Argonne, of course, Oak Ridge and NERSC, the 3 national labs which were interested in the exascale project at first. Georgia Tech, who helped us a lot with the prototype, both on the HIP side and on the CUDA side. The researchers from Parments, who has now been acquired by Intel, but were a startup company from the University of Tampere. Paganelsi, who is a former Intel employee that we have worked along during the project and is still working with us. He built his own company. And of course, industry partners, AMD, who were the developers of HIP, who helped us a lot in changing the ecosystem to accommodate our HIP implementation, and Intel, who helps us enabling features that were not originally supported, help with debugging our project, and help us converge toward a successful HIP project. So I will talk more about this part later in the presentation. So how does HIP work from a compiler perspective and a runtime perspective? So this is one of the single source, as in you're writing your kernels and your host code in a single source file, if you want. And then this file will be compiled several times for the host and for the device. We could also imagine compiling it for several devices. It's a C++ based language derived from CUDA. And both the kernels and device management can be in C++. The HIP-based API is a C API, mostly, which allows easy portability between compiler tool chains. So if you take HIP source code, a complicated project with several files, the idea is you will compile it once for the host and one for the device. That gives you LLVM intermediate representation for the host and for the device. So this is what the LLVM HIP frontend does. And then the host IR is compiled, in our case, with the LLVM x86 backend to give you an x86 binary plus HIP APIs, while the device IR are compiled with the LLVM AMD backend to AMD intermediate representation. Both of these are linked into an executable that embeds what we call a FAT binary, which contains the device code ready for execution on the device driver. And at runtime, through the HIP API on the right of the figure, the HIP library, which is based on ROCm, will execute these and dispatch your kernels to the device according to the program. So all of this compilation phase is done by a compiler called HIPCC, which is a wrapper above Clang. So what do we need to do in order to have chipStar function? So what are the extent of the modification we needed to do? They are mostly in two different aspects. We're keeping the multipass compilation, of course, but the idea is to have the library built on top of Level 0 and OpenCL, to replace the AMD IR by SPIR-V, which is a Kronos standard for heterogeneous intermediate representation of kernel code, and integrate ourselves into a modified HipCC, which will still leverage LLVM Lang infrastructure, but slightly modified HIP frontend that has been upstreamed. So most of our modifications are now in recent LLVM releases. So we've given back our modification to the community. We have additional LLVM passes to safely transform our device IR code, LLVM device IR code, to our SPIR-V IR representation. The translation is done thanks to the LLVM SPIR-V translator. That is a tool from Kronos, which is ported every new LLVM releases, which allows to transform the LLVM IR to SPIR-V. And so we have a modified HipCC wrapper script to pass a few specific options to LLVM Clang to allow communicating through a modified LLVM HIP frontend. But all of this is pretty minimal since we've been upstreaming most of the change, and when new ones are required, we then have a plan to upstream the new changes to the new version of LLVM. And of course, on the top right, we have implemented the HIP APIs on top of Level 0 and OpenCL. So this is how our project kind of transformed the HIP ecosystem from the compiler and library side of things. So we are talking a bit also about CUDA. So this is kind of a recap of the ecosystem. HIP applications can run on NVIDIA hardware through CUDA, on AMD through ROCm or HSA, which is the lowest level programming interface. And on Intel machines through either Level 0 or OpenCL. CUDA applications run on CUDA using the CUDA backend. You can use the ZLUDA project, or at least some versions of the ZLUDA project to run on AMD, directly a CUDA binary. But in our case, we support CUDA through recompilation of the application. And I will show you more about what we expect from our CUDA backend later in the presentation. So, what are we supporting in our HIP ecosystem? What can you use if you use our chipStar project? So it's available online on GitHub. It's pretty easy to find. I think we've mostly beaten the chip companies that are selling you fried potatoes. So we are kind of bubbling up Google ranking. We are fully built from open source components. So HIP command and HIP tests, which are results of our project, because these two repositories used to be merged with the HIP AMD backend. So thanks to our project, HIP is now split into three parts. We have the HIP command, which contain the headers and some of the old tests. The new HIP tests repository, which contain the unit tests for HIP, which are shared between the backends, as are the HIP command. And you have the HIP AMD repository, which contain the HIP AMD driver. And now you have chipStar, our Level 0 and OpenCL HIP implementation. So we need to thank AMD for working with us on this and accommodating our implementation and our open source implementation here. We leverage AMD ROCm device libs to create GPU instruction into LLVM IR. We support LLVM 15, 16, and 17, and we are in the process of supporting LLVM 19 as well. The pull requests are available online. And of course, we're using, as I mentioned, the SPAV LLVM translator that you can find on GitHub as well. So we have a GitHub Action CI that leverages the unit tests we've been talking about, plus a set of tests we've developed ourselves. We released version 1.1 in spring during early 2024, so maybe end of winter. I think it was February. It focused mainly on performance improvements. It's currently supported by ALCF through PagNRC, so Paulius Velasco, who is also an esteemed collaborator, and gracious contributions from Intel on the compiler side of the project and on porting some applications to it. We are working on version 1.2. We're expected to align to LLVM 19, and so it should take place sometimes in September. I will talk a bit more about our coming version. CUDA is experimentally supported, and we do so by converting CUDA calls to our HIP chipStar implementation. So it's pretty straightforward, and the CUDA implementation is pretty lightweight. All right, what do we support in terms of libraries that you can use in your project? So the idea is to provide the heap mass libraries that application require. Of course, we have very limited resources, so we focused on the most impactful one. But what is important is the one we support or actively supported. They are built on top of OpenCL. And we have a one API SQL interoperability built in our project to allow this. We design a unified architecture to abstract OpenCL and allow to build the heap libraries on top of it as seamlessly as possible. And I need to thank our Oak Ridge partners for this work. So we deliver to ECP, ePartC, HeapBlast, and HeapSolver. We are working on HeapFFT, HeapCub, and people have also been asking about HeapRend, which is something we are looking into. But you should have pretty good support from the first three libraries, the BLAST and the Solver. And we are currently very much pushing HeapFFT to try to embed it in some of our projects that require heap support. So what are the application heap sparse? That's a good question. We've looked into it. This is not on our priority yet, but if we have application that require it, depending on the extent, we can think about making a prototype. All right. Supported applications. The idea was to help ECP, ESP, and others to use heap on Aurora during the ECP project, and we are continuing with this effort by engaging new application team. So we have functional applications where we are optimizing performance. So several of the CP2K apps are supported, and we are working on an application that requires HeapFFT. So this one is in progress. We have support for 98% of libseed, I think, meaning that 98% of libseed unit tests are passing on our implementation. Some quirks exist for some kernels on people using some patterns people use in kernels. And we have support for games, and Colin can tell you more about it, and there are more slides in the presentation. But yeah, Colin did most of the game porting. ECP was working with Exabiome, so these were our colleague from NERSC. This is kind of paused at the moment, but we still hope to continue engaging. And we have prospective collaborations with the TLSH project, which are using HIP, which would be interesting to bring to our platform. OpenMM reached out to us recently to try and help them. And also private companies may also reach out to us sometimes. So we are working with people to try and broaden our scope. I need to also talk about limitations. So if you're trying to port your project to chipStar, most probably you may encounter issues. And so there are a limited set of issues you usually encounter, so I thought it would be interesting to go through them so you're not surprised. So we have a few limitations on the kernel, and they apply to SYCL as well, meaning that if you choose to port your application through HIP or to go to SYCL, the same kind of modification to kernels will need to take place. So group function, especially masked group functions where all the threads are not participating to the operations, are not supported because of hardware limitations. The most striking example is the 3-argument shuffles instructions that exist in CUDA and HIP. So this one we encountered a couple of times. You need to rework the algorithm to have all the threads participate in the shuffle. Early exit from thread also can cause issue, especially if they are combined with barriers. So we are trying to work on compiled passes to alleviate this. But the idea is that on Intel hardware, if all threads do not participate in the barrier will wait. Whereas on CUDA, thread that already existed will be considered always participating in the barrier. It's a simple explanation, but it's simple one-term model, but it helps understanding what the issue is. So we're trying to work on compiled passes to alleviate the simplest cases, but the general solution is maybe not attainable this way. And of course, missing library is also a big hurdle. So we can support new libraries. We are working on some new libraries. The idea is that if it's in Intel OpenCL, most probably it's pretty straightforward to port. And Intel has provided other libraries that map one-to-one with CUDA, but they usually or may depend on the different kind of programming models and may be a bit tricky. So it's a bit more effort to port libraries which are not based on OpenCL. And of course, you can encounter bugs. Please report bugs and missing features, which we consider bugs, to the project. We will address them. Of course, we do not support 100% of the YEP APIs, so we've prioritized our support by application usage. So our graph support is pretty limited at the moment, but we have found applications that were making use of them. So it's not been a high priority, and we've rather wanted to work on stabilizing the project, improving performance and fixing bugs than working on features nobody are using. But of course, if your application requires it, it will increase the priority of this support. So I'm going to present kind of the results we obtained at the end of the ECP project on benchmarking our implementation. So the idea was we wanted to be able to compare our implementation with other programming models. We wanted a broad coverage of our feature sets, and the idea was to use the Headbench benchmark set from Deming, who is working at ALCF now. But he did an incredible collection of benchmarks, gathering open source benchmarks from the web, porting them to different programming models so you could compare them. And the idea is to assess our functionality by looking at our success rate inside this benchmark set, report the bugs, of course, and assess our performance and comparing it to SQL to see if we were competitive on Intel GPUs. So first, the heap API version of our comparison. So we worked on the full 261 heap benchmarks, which are contained in Headbench. So not all of those benchmarks contain verification of the results and timing codes. As we go deeper into the analysis, we are dropping tests because we cannot verify that they run correctly, and we cannot check that the performance is indeed what we're looking at, because sometimes comparing the runtime of the full benchmark, since it embeds the comparison code for the results validation, or some compilation that we could offline, may not be a fair comparison. So we only compare performance when we know we're doing a fair comparison between the programming models. So we can compile 90% more or less of these benchmarks, run 85% of these are compiled successfully, and for those that had result verification, more than 90% of these passed. The errors are Intel runtime errors that we are addressing, hangs, which are usually due to kernels with some of the problematic patterns, and incorrect answers, which may be due to race condition or kernels that do not respect the supported semantic on Intel GPUs. So if we want to compare heap and SQL on PVCs, their performance, we can do the ratio of the benchmarks between the heap and the SQL version. So on the left, you have the benchmarks that behave better on heap. And on the right, you have the benchmarks that behave better on SQL. So this is on the PVC GPU, on the Vecchio GPUs that are present on Aurora. And as you can see, the S-curve is pretty flat, so the performance are mostly comparable. We have outliers, of course, and we are working on reducing these gaps. We've had Jenny Chen, an intern at ALCF. She interned twice, so you will see more of her work later in the presentation. Work on our Gen 9 GPUs, which are open to anybody who wants to try, whereas PVC was under NDA for a very long time. So Jenny worked on our Gen 9 GPUs, which are still available on GLSC. And she used the subset of Headbench benchmark that were precise on timing and included verification in order to compare the performance between the two. And the outliers were investigated, and after fixes, both on the SQL side of things and on the heap side of things, most often on the runtime, but sometimes also on the compiler, we've managed to bring these benchmarks to usually more acceptable performance ratios. So this work not only enabled us to improve heap, as was the goal, but it also enabled us to improve the heap, backend, and compiler in order to fix some of the discrepancies we were seeing in those benchmarks. So it's been very useful. So a little preview. Jenny came back this year. She worked on the CUDA support for bench. And so this couple of slides presents the results she got this summer. So the presentation is a bit different this time around. So to give you an idea of what we had to do in order to pass those benchmarks. So first, when Jenny started, none of the benchmarks would run because the NVCC wrapper script we had prepared was problematic. So Jenny, with the help of Paulius, fixed the NVCC compiler for chipStar. It allowed us to start running the benchmarks, but Jenny focused on benchmarks where she could validate that they were working correctly. Oh, sorry, I missed this question, Kevin. I can go back on the slide. So from the runtime perspective, it was on our side event handling and the usage of immediate versus regular command lists. On SQL, there were some event-related performance optimization that were created. And one of the other improvement on the SQL side of things were mem copies who were improperly optimized. And we discovered this during one of the benchmark, and we made sure with the Intel compiler team that the mem copies were correctly optimized. So this is the kind of optimization we've been doing both for heap and for SQL in this context. To give you a precise list of all the ones we did, I would need to look through the PRs and the deliverable of the project. But that's to give you an idea of the kind of optimization we did.
Yeah, I think for those specific ones, Jenny has some information in the poster, and I will put the little summary of that in the chat.
Thanks a lot, Colin. All right. So on the CUDA side of things, once the compiler was fixed, Jenny started working on the benchmark that could be validated this time around. And there are many, many CUDA benchmarks. There are more than 300 CUDA benchmarks in Bench. So not all of them have been ported to other programming models. It's a work in progress. But Jenny found 180 of these that could have validated results, which were very important for us in order to measure our coverage. And so she did a first evaluation pass. So of these 180 benchmarks, 90% almost compiled successfully at first. Out of those 90%, from these 180, 81 run successfully. So 90% compile and 81% of the total run. And 90% of those which were validating passed at first. And then Jenny went and digged through the errors. She did some fixing, she proposed solution, she reported the issue she couldn't fix. She made pull requests. And the result was that now the compilation rate is up to 96%, the running rate is up to 89%, and the passing rate when we have the validation required is 99%. So she got great results here, and the CUDA support looks way better than when she started. So this is the overall results from the previous graph, from the compilation. So the errors during runtime are either timeouts or runtime errors. Timeouts are usually hangs on the GPU. They can also be in the runtime, but they are less likely. We have much better confidence in our runtime nowadays than we used to. But we can still encounter bug here and there. And of course, the passing rate is pretty great. So we are not generating invalid results. Only in one case, and I don't remember what was the reason for this one. All right, let's talk about real application. So here we are going to talk about games, which is General Atomic and Molecular Electronic Structure System. It's a quantum chemistry code. It contains CUDA and heap library that target Summit and Frontier. And the idea was to use chipStar to port the R3 method. So it's tens of thousands of lines of kernel code, blast calls and solver calls. The list is given here. I will not go through them. We use shared memory. We use barriers inside the kernels to ensure atomicity, and race conditions are met and not met, well, are avoided. So it was pretty involved. But as Colin notes here, the porting effort was relatively low. We didn't have to be too intrusive on the build files. So meaning that we have CMake integration that works. The thread synchronization issues I was talking about was one of our issues. So early exit was a pattern that was used in the code. And this can lead to deadlock on Intel GPUs. So the code still works better on A100 than it does on half of a PVC GPU, one time. But we are not order of magnitude. And AMD is working on solving the eigensolve heap blast command being pretty slow on AMD hardware. But this is our current performance results. This is on level 0 because we are investigating performance difference with OpenCL. So we are still working on improving the performance of games here. We're not completely satisfied, but this is a great beginning. So if you want to use chipStar, you can try it. And I will show you in these slides how to try it on 2 of our platforms, GLSE or Sunspot. It is pretty similar, but I want you to be able to refer to these, and I will thank Colin for putting these slides together once more. So on GLSE, the first step is, of course, to acquire a node using your project. I don't know if we can still do 120 minutes request. I think we can do on Iris, but not on PVC. We used to be able to do 6 hours on Iris. It was awesome. So grab a node for a few hours, load, use the right module files. So these are directly installed system-wide. You can load then our chipStar. I advise you to try our 1.2 preview version. since you will get most of our fixes and performance improvements. And then you can try cloning the heap training repository and try our most simple example at first, which should get you started. So just make should work. It contains a CUDA and heap CUDA SAXP examples, which are really simple to understand. You will get a small warning about NVCC compilation because it's still a work in progress. But then you can run your binary you obtained, and you will see and you will check that the vector operation performed correctly. So this is really straightforward, and you see the commands are only using heapcc and NVCC, and it works straight out of the box to compile a regular CUDA or heap code that you could have compiled with AMD or CUDA equivalent. On Sunspot, so the access is a bit more restricted, but you should be able to grab an account, provided you can sign the NDA. You will need to grab a node. Same thing here. One of the difference here is that the modules are in Colin's home folder because we do not have root access on Sunspot. And Paulius also provides builds in his own folder. So you can you have two sources of module files you can use. I advise then again to use our 1.2 preview chipStar version, and the rest of the instructions are similar. Clone the repository and compile the example. They should not give you any errors. If you want to ascertain you're running on the GPU, one tool you can use is our lightweight iProf tracer. So some of you may be familiar with it. The only difference is you need to give it the name of the heap library you want to trace. So by default, it uses a AMD heap64 name. We've decided against doing that in the chipStar project because both were not AMD, and also we didn't want any application linking with us mistakenly. So we rename our library libchip. So you need to tell iProf that it's going to trace libchip, but then you can run your SAXP heap example, and it will show you the commands. So you see that the heap and level 0 commands are listed, which means that you are using the level 0 backend by default on our platform, and this is expected. You can switch to OpenCL by using an environment variable that our heap runtime will catch. And you don't need to recompile if you want to try the OpenCL backend. Just by using an environment variable, we could switch to OpenCL. So our iProf tool also allows you to get a timeline of what is executing if you want to understand a bit better how our heap implementation is working. So it's working with Perfetto framework from Google. So this is a capture of a Chrome screen. So it's a Chrome screenshot of Perfetto where you can see heap commands get translated to level 0 commands. On the bottom, you have the GPU executing one of the kernel. And you can see that we have a second thread which is currently checking the status of an event here. So it's pretty useful for us to debug and to instrument our runtime, but it's also very useful for applications, try to understand. And we've used it several times to optimize both applications, but also the different runtimes. And we use the same tool, of course, for CUDA to understand how CUDA or OpenMP are implemented in the Intel compilers. Okay, a little slide about how to install chipStar. It's pretty straightforward. So if you want to try it on your own computer, you can find the instruction in this link. Just to give you a slight overview of the steps, you need development file for OpenCL and or level 0, of course. You need a working OpenCL and level 0 device driver. Note that you can use a CPU OpenCL implementation from either Intel or PoCL, and it will work. Optionally, you can install one API and one MKL if you want SQL interoperability and access to the math libraries. The steps are pretty straightforward from there. You build LLVM Clang with SPIR-V LLVM translators. These steps are described in the instruction above. And then you build and install chipStar using this Clang compiler you've just created. Optionally, you can build additional math libraries. So it's a 3-step, and Jenny, our intern that was there this year, she's a second-year intern at university. She was able to do it by herself on our first or second day of internship. So it's pretty straightforward. So a bit of conclusion here. So chipStar for Aurora. We delivered for ACP chipStar 1.0. So for those of you who were with us on the ACP project, this was 15 milestones with all the partners involved, a working EP implementation with support for selected applications and libraries, competitive performance with cycles. So this was our objectives. We then continued working after ACP on chipStar 1.1, focusing on performance improvement, thanks to the support from ALCF. I would like to thank Mike again for the continued support. We are still working. We have an upcoming in chipStar 1.2. We have this experimental CUDA support that is now maturing. We'll keep working on improving performance and stability. We're deploying our releases on our platform, so you can leverage level 0 OpenCL on Sunspot, on GLC, and soon on Aurora. It works on your laptop if you have an Intel GPU. It works everywhere if you use PoCL or the Intel OpenCL driver. So if you have an x86 CPU, you can use the Intel OpenCL driver as well. And perspective, so of course, CUDA is still on the to-do list. It's experimental but promising. So we'd like to continue, especially since the other CUDA projects, which we're trying to have binary compatibility with CUDA, have been met with setbacks. So ours is a more conservative approach, but it's most probably can work. We're looking to support more applications by collaborating with ECP and ESP teams, but also people from outside are welcome to come with their application, and we can help them and study the gaps. New features, so HIP is constantly evolving. So we're focusing, I told you, on application requirement. The best way to steer the development is to come with your application and tell us what we're missing. The libraries which is required by the application are still in development. And also what we are actively doing is trying to extend the OpenCL and SPIR-V ecosystems to better support HIP and CUDA. So inside the Chronos working group, I'm personally working with Intel and ARM on defining new extensions to allow OpenCL, SPIR-V, and level 0 to better support HIP and CUDA. So we can reduce the gap we've been talking about during this presentation. So we are working with ARM and supporting it. This is a work in progress. And we are working on making Aurora work on Rustical, which is the Mesa OpenCL implementation, which is available on a wide variety of hardware and which is giving very interesting performance. And we have results in an upcoming journal paper we're working on. We are looking for additional funding because we have only enough funding to continue funding PAG-LLC for now. So we are looking through a seedling project to try and get funding, specifically through the S4PST, which is a CIS4 System and Programming Environment project, which embed compilers and MPI runtime and so on. So we're trying to get funding through this one in order to expand our development work. And of course, the usual acknowledgements. So this research was done thanks to Argonne Leadership Computing Facility, GRC, of course, and the Exascale Computing Project. And this concludes my presentation. If you have any questions, I think we have a few more minutes, and I'd be happy to answer.
Thank you, Brice. Yeah, I see a lot of questions, and thanks for calling. Most of them have been answered, I think.
Thank you very much, Colin.
Yeah, I think the one, last question that Colin also is answering is about if the chipStar can be extended to other languages than C++.
So from the runtime perspective, we are almost binary compatible. The real question is, these things become increasingly easier when languages leverage LLVM. So you could target our implementation by transforming your LLVM IR that you generate from your own different language into SPIR-V, and then feeding that through the heap or CUDA backend. So this would be a viable strategy to support a new language. I don't know what language you were specifically thinking about.
So I think he's asking about AI and Python, like AI framework, so Python, for example.
Yeah, so in this case, those are, as was entered in the chat, based on C++. So they are interfacing with C++. There are other attempts, especially Rust, is starting to write language for support for programming languages such as CUDA or OpenCL, using SPIR-V directly by leveraging the LLVM to SPIR-V computation flow. We are currently working in the OpenCL working group. Members of the OpenCL working group are working, and Vulkan working group are working on putting a real SPIR-V backend in LLVM, which should make this project even simpler. So yes, there is hope to bring support to new languages.
Thank you. I see Filippo's hands up, so feel free to unmute yourself and ask question.
Hello, thank you for the presentation. So I've actually maybe two questions. One is related to the previous one. So have you tried to use chipStar to kind of port many of the, I guess, Python libraries that have like a CUDA component, and some of those are not usable on Intel GPUs, and maybe this could be a good tool for translating those. And then the second question is, what is the difference between your approach and other tools like Cyclomatic or deep CP++ compatibility tools?
Okay. So the first answer to the question is yes, we've tried. So we have a port of PyTorch that works, at least for a subset of the PyTorch functionalities that were interesting. So Intel took care of that and they made it public, but I can't tell you much more about it. We've been approached by other frameworks, and we're looking at the gaps, which are mostly in libraries. So some of them use hipsparse, so we don't support hipsparse yet. Some of them use ROC version of the libraries, not the hip version of the libraries. So depending on how they targeted the AMD, it's different. We have not tried direct CUDA support for now, since it's still experimental. So we've mostly worked on hip backends in this project. But we've seen some success, especially with PyTorch. The second aspect of your question, could you repeat it, please?
The difference between other tools like
Oh, yes.
Diplomatic and the C++ compatibility.
So these tools do translation of source to source to transform a HIP program into a SQL program. Our approach is completely different. What we're doing is we are compiling a HIP program directly, and we're implementing the HIP APIs. So we are a real implementation of HIP. So we are not transforming the code at any point. What we are transforming is the intermediate representation in order to translate them to SPIRV. But it's just the fact that we cannot ingest AMD intermediate representation. The third kind of tool that exists, which has a different approach, is binary compatibility tool. They mostly have been tried for CUDA, and the idea is to ingest the PTX that the CUDA compiler generates. So the implementation of the library is the same aspect, but on the compiler side, the idea is to take the binary, read the PTX directly at the application runtime, and translate this PTX to SPIRV using LLVM. But this approach, NVIDIA is not really keen on, and they are trying to prevent them. So it's difficult for a big company to invest time on this because it's felt as dangerous from a legal perspective. So we don't have native CUDA support. We recompile CUDA applications, which is meaning you can't run your binary CUDA application on chipStar. You need to recompile the CUDA application if you want to use it with chipStar. And this support is experimental. Hopefully that answered your question.
Yes, thank you.
Are there any more questions? I see a couple of conversations. That Colin's already responded. Any more questions? Yes. If not, I would like to thank Brice and also Colin for helping in answering questions. We will provide the slides and also the recording. Thank you all for attending this session. I hope this was a useful discussion. And thank you, Brice and Colin, for being here with us today.
Thank you very much, Yassi. Thanks everybody for attending. Bye-bye.